Here's another simple problem on using the Faraday's law. Faraday's law is EMF equals minus n d dt of the magnetic flux. We usually ignore n. And so, but the equation you need for these problems here is E that the L, where you integrate electric field along the edge of a surface, and it's got to be a closed loop, equals minus, well, you would have n in here, but I think for the problem that we're about to solve, this n is not needed, so you would just have d dt, and then you have b dot dA. This is the magnetic flux, and you integrate, you figure out the magnetic flux through surface S. So these two S's, this S and this S, refer to the same surface. It's just that on the left hand side you integrate along the edge of the surface, and on the right hand side you integrate through the area of the surface. So number 39, page 984. Oh, look at that, we're almost at page 1000. Huh. This is really a continuation of number 38, so I think it makes sense to solve number 38 first and then look at number 39, because there's a certain continuation, and I'll move a little faster through this problem because I'm going to assume you have seen the problem number 38. So what we have is a solenoid again. I'm going to draw it like this. Here's a solenoid, and then there's a current through this solenoid, so there's a current I, and let's pick a direction. Here's the current I, and it's not a steady current. The current is changing, it's increasing, and in fact what we are looking for is this di dt. This is the unknown. And what the problem gives us is the electric field at a specific location. So they tell us is that the electric field at a specific point has a specific value, find the I dt. In number 38, you were given the I dt and you were asked for electric field at a specific point. So 38 is a reverse. I'm going to put here, this is a reverse of number 38. So you should try this problem first, solve it on your own, and then come back and see how I did it. Let's put your face here again. So this is this is you. Give you an ear, some eye here, and you're looking at this solenoid here. And if you look at that solenoid there, then the picture you would see is this. And let's actually refer to this picture from now on. The magnetic field is going to, if this is how I drew this whole thing, then magnetic field comes in this, goes in this direction, loops around. Magnetic field here goes in this direction, loops around. That's how I drew it. And so then I have magnetic field that comes out of the page here. That's the magnetic field B, comes out of the page towards you, and then the current I is flowing in this direction, and this current is increasing. And the increasing current here, the change here is the increasing current, which of course implies there's also increasing magnetic field. The system will oppose that change, so it's going to set up an electric field that points in the direction that opposes that change. This is how you can actually, this is basically Lenz's law. So in a sense, we have sort of mentioned it here, but the electric field here, taken from what I just said a second ago, and from number 38, is going to point in this direction. And it's going to be stronger here and even stronger over here. And then along this line here, electric field will point like this, and then like this. Along this line here, electric field will point this direction, even stronger there, and then maybe along this one here, electric field would point like this. And I think that'll do. Of course, if I wanted to, I could draw a few more. You know, I could draw along electric field along this here, so that I would have electric field doing this, and yeah, why not? Since I started it. And then maybe I'll do electric field here and electric field here. Right, and there's of course electric field inside as well. Okay, so we have the electric field at points like that. As the magnetic field is coming out of the page, it's increasing that increasing magnetic field. So increasing magnetic field is going to give us an electric field which opposes the change, and that's how we figure out the direction of that. But and then what's given to us in this specific problem is that the electric field at a specific location. So this is r. R is the radius, starts from 0 and just goes out to some point. Could be within the circle, within the solenoid, could be outside of the solenoid. It's just r being distance from radial distance from the center of the solenoid. What the problem gives us is that the electric field at a very specific point, namely r equals, where is it? Uh, 3.5 centimeters from the center. So at r equals 3.5 centimeters, the electric field is 8 times 10 to the minus 6th. 8 times 10 to the minus 6th volts per meter. All right. So volts per meter are units of the electric field, and maybe on a side, just in case you forgot, volts per meter is the same thing as newtons per coulomb. Both units of the electric field are fine to state on quizzes and tests. So this is what we have, and the question is, let's state the unknown. The unknown is, what is I dt? At what rate is the current changing? Okay, so let's start from this equation and let's work this thing backwards. And so what we have is E dot dl, where I integrate along the edge of a surface S, and of course the surface S is this. This is the surface S. It's this whole area here within the loop. Right, so all of this here, that's my surface S. So this is the left-hand side of the equation. The right-hand side is minus d dt, and then I have b dot dA, and I integrate through the area of the surface S. The left-hand side, well, the electric field, from the picture I gave you, it's actually fairly easy to see that the electric field is parallel to dl. Since I'm going to integrate, dl, let's see if I can put dl here. I'm going to start at I can start at any point I want to, but I could start here and then move in this direction. Here's dl, and then here's another dl, and then here's another dl, until I complete the full circle all the way around. And in that sense, dl is parallel to E, right? dl and E point in the same direction at every point along this circle here. dl and E are parallel. So the left-hand side then just becomes EDL. And the electric field, okay, so let's write this minus d dt, and this is b times dA. And now, but the electric field is constant. Electric field is constant, at least from the picture I drew. It is constant it is always the same at a certain specific distance away from the center. It is constant. It's not constant everywhere, right? So for example, electric field at this point has a certain value, but at this point has a different value. At this point has a different value. But the electric field along this path here has the same value everywhere. The magnitude of the electric field along this circular path is the same, and that's really what I need. And this is what I mean by electric field is constant. It's constant along the integration path, along the dl. So if it's constant, I can just pull this out, and I have dl, and then I just integrate through the whole path, and that would be from 0 to L. Equals, and then the right hand side d dt of, well, let's do a little bit here, a little bit of work here. So b dot all right, b dot dA. So figure out the left hand side, that's just the electric field times 2 pi r, because the path length is just the circumference of the circle that I take. On the right hand side, I get d dt of the BDA, right? BDA. Okay, so the A vector points, here's the loop, A vector points in this direction, it's perpendicular to the surface, and of course A here is parallel, A vector is parallel to to the B vector. And so in that sense, the dot product just sort of becomes the very straightforward one, be that dA equals B dA cosine of 0. Cosine of 0 is 1. So I have that, and then the next thing to realize is that the magnetic field B, well, it changes in time, but it doesn't depend on X or Y or Z. Magnetic field is the same at a specific instant in time. Magnetic field is the same everywhere on the inside of the solenoid. And so what I can do here is I can just pull this B out. So this is minus D dt B dA. Put this in parentheses, and of course this becomes how about I move this whole thing somewhere here. So the electric field times 2 pi r equals minus D dt B times A, where A is just pi r squared. We did exactly the same thing in number 38, but I guess I figured I would do it again so that you can see it done again. At some point you become familiar with these problems after you've seen enough of them. And this whole thing becomes minus pi r squared d dt. There's no need for partials anymore. And from here I'll move up. So pi goes away, r gets simplified a little. I have E times 2 equals minus r times dB dt. But the magnetic field on the inside of the solenoid is just mu naught times n times I. Of course, mu naught times n is, these are constants, and then I is the thing that changes, varies here. So what I have is that the electric field times 2 over r, I guess I'll bring minus to this side, equals mu naught times n times dI t, and I'm almost done. So what I have here is that the electric field times 2 over mu naught times n times r equals, where am I? Oh yeah, equals dI dt. So let's plug in the numbers, and that will do for this problem. So the electric field, so this is it. This is the expression for dI dt. Now, of course, remember that this electric field here depends on r. And so if you were to actually go ahead and solve this problem numerically and find numerical solution to this, what you would have to do is you would have to put, for the electric field, you would substitute the given. So 8 times 10 to the minus 6th times 2 divided by mu naught, that's 4 pi times 10 to the minus 7th times n. N was given to us. I didn't state it, but n was given to us. N was the density of the loops, and for number 39, that was 400 turns per meter, so times 400. So maybe I'll add that piece of information. N is 400 turns per meter. And so then times r, well, what's my r? Well, r is the same at which I measured the electric field. And so this has to be 3.5 centimeters, so 0.035 equals dI dt. So I guess in the last step, the only tricky part is to remember, to make sure that the value of the electric field here corresponds to the value of the radius at which you measured that electric field in. And if you were to go on, you would then calculate and find that dI dt equals, well, just a matter of plugging in the numbers. Whatever you get for that would be the answer, and that would be amps per second. I guess I'll calculate it. So I got 0.91 amps. All right, here's your simple problem.